Hello everyone, myself Sinchana BS. I am studying in SVCE Bangalore. I am pursuing with 4th semester CSC Engineering. Now I am going to talk about Dijkstra'S Algorithm. Next is introduction about Dijkstra'S Algorithm. Dijkstra'S Algorithm is a popular algorithm used to find the shortest paths between nodes in a graph. It was conceived by Dutch computer scientist Dijkstra'S Dijkstra's in 1956 and published 3 years later. The algorithm is widely used in GPS systems and network routing protocols to optimize pathfinding. Dijkstra's algorithm is a graph search algorithm used to find the shortest path between nodes in a weighted graph. It was developed by Dutch computer scientist Edster W. Dijkstra's in 1956 and published in 1959. The algorithm is widely used in routing and navigation systems. And next one is graph representation in Dijkstra's algorithm. Dijkstra's algorithm operates on weighted graphs where edges have associated costs. Each node vertex has a list of its neighboring nodes and the weights of the connecting edges. Efficient for sparse graphs. The graph can be represented using an adjacency matrix or an adjacency list for efficiency. Nodes represent various points while edges illustrate the connections and their respective weights. And next one is algorithm overview. The algorithm maintains a set of nodes whose shortest distance from the source is known. It repeatedly selects the node with the smallest known distance and updates the distance of its neighbors. Set the distance to the starting node as 0 and all others as infinity. Mark all nodes as unvisited. Use a priority queue 0 minimum heap to always select the unvisited node with the smallest known distance. This process continues until all nodes have been processed or the shortest paths to the desired nodes are found. This is the graph of Dijkstra's algorithm. Next one is steps of the algorithm. Start with initialization. Choose the node with the smallest tentative distance. Update neighboring nodes. Once all neighbors are checked, mark the current node as visited. A visited node will not be checked again. Repeat steps 2 to 4 until all nodes have been visited or the destination node as smallest distance in the unvisited set. When all nodes are visited or the shortest path to the target node is found. The algorithm stops the shortest path tree or distance from source is now complete. Dijkstra's algorithm finds the shortest path from a starting node to all other nodes in a graph with non-negative edges weights. Here step-by-step breakdown. Initialization. Assign a distance of 0 to the starting nodes and infinity to all other nodes. Mark all nodes as unvisited. Then iterations. Select the unvisited node with the smallest distance. For each unvisited neighbors of the current node, calculate the tentative distance to the neighbors through the current node. Next, if the tentative distance is less than the current distance to the neighbors, update the neighbors distance. Mark the current node is visited. Then repeat, continue iterating until all nodes have been visited. This is the step-by-step step of the algorithm. And next one is priority queue implementation. A priority queue is circular for optimizing Dijkstra's algorithm, allowing efficient extraction of the minimum distance node. The priority queue can be implemented using a binary heap which provides logarithmic time complexity for insertions and deletions. This implementation significantly reduces the overall time complexity of the algorithm. In Dijkstra's algorithm, a priority queue significantly optimizes the process of finding the shortest paths in a graph. It efficiently manages the exploration of vertices based on their current shortest distance from the source. Here how it works. Initialization. A priority queue stores vertices and their current shortest distance. Elimination. The source vertex is added with a distance of 0 while all others are initially marked with infinity. Next one is iteration. The algorithm repeatedly extracts the vertex with the minimum distance from the priority queue. Next one is exploration. It then examines the neighbors of this vertex. For each neighbors, it checks if a shortest path to neighbor can be found through the current vertex. Then next one is update. Update if a shortest path, and next is termination. The process continues until the priority queue is empty or all vertices have been finalized. Next one is benefits of using priority queuing. Efficiency. The next slide is time complexity. The time complexity of Dijkstra's algorithm depends on the data structure used for the priority queue. Using a simple array leads to a complexity of 0, V or 2, where V is the number of vertices. However, with a binary heap, the complexity improves to V plus E log V, where E is the number of edges. Using an adjacency matrix without a heap negative approach, time complexity 0 V square, suitable only for a small or dense graph. And next is limitations of Dijkstra's algorithm. Dijkstra's algorithm does not work with graphs that contain negative weight edges. It can lead to incorrect result if a negative edge weight is present in the graph. For graph with negative weights, the Bellman-Ford algorithm is a more suitable alternative. Cannot handle negative weights, insufficient for large graph without optimization. Only finds the shortest path from one source. Doesn't work well in dynamic. Dijkstra's algorithm can be modified and extended in three main ways: by alternating how distance is defined by using different data structures, and by changing the relaxation and distance initialization methods. These three variations lead to different applications and performance characteristics. Here more detail about breakdown. Distance definition. Standard, the most common definition is the Euclidean distance, or the total cost of the path in a weighted graph. Custom distance can be redefined to present other factors such as time, traffic, concurrency, or even a combination of factors. Data structure. Priority queue. Dijkstra's algorithm typically uses a priority queue to efficiently select the node with smallest distance from the source. A set can also be used to maintain visited nodes. List. In simpler cases, a list might be used, but it's less efficient than a priority queue. And next one is applications of Dijkstra's algorithm. Dijkstra's algorithm is widely used in mapping and navigation software to find optimal routes. It is also utilized in network routing to determine the best paths for transformation. Other applications include robotics and game development for pathfinding algorithms. And next is variants of Dijkstra's algorithm. There are several variants of Dijkstra's algorithm, including bidirectional search for improved efficiency. Your second bullet search algorithm combines Dijkstra's algorithm with heuristics to enhance pathfinding in certain scenarios. And next one is conclusion. Dijkstra's algorithm remains a fundamental concept in computer science and operations research. Its efficiency and simplicity make it a preferred choice for many real-world applications. Understanding this algorithm is crucial for those entering fields such as data analysis, AI, and network design. Thanks for watching my video.